Hi everyone. Today we're going to be going through neutralization and titrations. This will be lesson 5.9. So neutralization reactions are ones that you already know about, and titrations, that may be a new concept for you, but we'll have a lab on this and it'll make sense to everyone. So neutralization, again, this is a review technically from grade 10, and then you would have talked about it again briefly in grade 11, and then in our first unit in grade 12 here as well. So this is when an acid and a base react. They are going to form a salt plus water, right? So if this is our acid, this is our base, this will be our salt, and then of course the H2O is our water. So salt we're used to seeing as NaCl, but the word salt is a more general term in chemistry, and we can think of it as the compound that is made when you have the neutralization reaction between an acid and a base. So if we had an acid solution with an unknown concentration, basically we can use this reaction in our mole ratios to solve for an unknown concentration. So if this is your unknown, but you know the concentration of this base, for example, once you've reached a neutralization point, you can use the balanced equation to solve and to figure out the molarity of that unknown acid. Okay, so for example, we've got HCl here, so HCl and sodium hydroxide are going to bond or neutralize to form sodium chloride, so the salt plus our water. So for example here, it would take 1 mole of sodium hydroxide to neutralize 1 mole of HCl completely. So we're following the mole ratios, and remember these are ones in front there, so this particular reaction is a 1-to-1 ratio. If we look at this one, we've got our magnesium hydroxide and the HCl. Bonding to make magnesium chloride and water. These are double displacement reactions, right? So it would take 1 mole of the magnesium hydroxide to neutralize 2 moles of HCl. So here our ratio is 1 to 2. So yeah, we're always going to use the molar ratios to solve these problems here. Okay. So this is the titration setup here, and you can do a little sketch in your notes of this so you know where things are. Normally this would be set up so that you would have, it's written here as the acid, but it could be an acid or a base, it doesn't really matter. But let's say in this one we've got our acid in our flask here, and this is an Erlenmeyer flask, and normally we would use a flask instead of a beaker because you want to kind of swirl it throughout the titration procedure, and just with that smaller neck there, you're less likely to spill. Okay, so you would use an Erlenmeyer there. You would swirl it. This is your burette, this thing here. This is called the stopcock, and so you're going to be able to control the flow of the base going into the acid to neutralize it. So the burette has gradients here where you can read off the volume. So this is a pretty precise way to show how much base you're putting into the acid solution. Okay, so how you're going to do this, you can copy this stuff down, but really we need to like do the lab for this to really get a feel for what's going on here. So a known volume of an acid or a known concentration, a known volume of an acid of unknown concentration. So the volume is known, but the concentration is not, and you have to make sure of that. Is added to a flask. Often you'll add some water in there after it to just make the color changes easier to see. Now we're going to add a few drops of indicator as well. The solution normally would be colorless at this point. So if we use phenolphthalein as our indicator, it would be colorless. A burette then is filled with a base of known concentration. So this is called the titrant. So you're going to put the base inside this burette here. You're going to fill it up, and that is called the titrant. The titrant is added to the flask until the equivalence point. So some new language here, so make sure you're picking that up. So equivalence point is known as the neutralization point, and we know that happens we know that we've reached that when we see a change in color. So phenolphthalein is going to change color right around pH 7 to 8. So that tells us that we have reached that neutralization point. And so we're going to be looking for a very pale pink color to show up in our solution. So when we see this color change happen, this is the neutralization point. So at that particular point, we know that the moles of H plus are going to be equal to the moles of OH minus. Okay, so we've got our acid equaling our base here, so that hence the neutralization point here. Now from here, you're going to use the mole ratio to find the concentration of the unknown acid. And so this essentially goes back to grade 11. In your solutions unit, you may have done problems like this, maybe not, but the chemistry or the math involved is really just a grade 11 concept. So this whole lesson today is really grade 11 and just adding in the procedural part of the titration to it. Okay, so we're going to work through this problem here. So a volume of 18.28 milliliters of a standard solution of 0.100 molar NaOH is required to neutralize 25 mils of methanoic acid. So what was the initial molarity of the acid solution? So like most chemistry problems, I like to keep track of my information underneath the equation so I can really clearly see everything. And I know that it takes 18.28 milliliters of 0.100 molar sodium hydroxide, and that neutralizes 25.0 mils of methanoic acid, and I'm asked to find the concentration. Now, if you'll remember the formula for concentration, M equals moles per liter, right? So looking at that for methanoic acid, I've got the volume, but I don't have the moles. So I need to calculate that, and I'm going to find that by looking at the sodium hydroxide. So if I look at the sodium hydroxide here, I've got a volume and I've got a concentration, so I can calculate the moles of sodium hydroxide. So I'm going to go ahead and do that. So moles of NaOH is going to be equal to molarity times liters. So I just rearranged that equation to find that. So this is going to be 0.100 multiplied by 0.01828, because I'm going to change that into liters. And I get an answer of 1.828 times 10 to the negative 3 moles of sodium hydroxide. Now, at the neutralization point, I know that moles of OH minus is going to equal moles of H plus. So that tells me that that's what I'm stumbling over my words, sorry. So that tells me that I know how many moles of methanoic acid I have here at my neutralization point. Now the mole ratio is 1:1. So I can, if it wasn't 1:1, you could use dimensional analysis to figure that out, or just know that you have to multiply it by 2 or whatever it is, right? But ratio is 1:1. So what that tells me is that I'm also going to have 1.828 times 10 to the negative 3 moles of the methanoic acid here. So now I've got the moles of methanoic acid and I've got the volume. So I'm going to go back to this equation here and I'm going to sub these in. So 1.828 times 10 to the negative 3 all over 0.0250. And I end up with an answer of 7 and I need 3 sig figs here because of that. So 7.31 times 10 to the negative 2 molar, or moles per liter, and that would be my answer here for this particular question. So as you can see, this is really just a grade 11 concept here, right? Just using the concepts of concentration and then applying the mole ratio to it. Okay, now there's a lot of assignments on this. They're all very similar though, so like I said, I would not do all of these assignments. I would pick and choose a few questions maybe from each, or just scan them over, see how they look to you. But 35, 36, 37, 38 are all sort of the same concepts here, so take a look at that. Okay, thanks everyone.